Thank you. So our next speaker is online, I think. Dr. Wang from Yale University. I'm sorry, I don't know whether I need to do anything. Okay, great. So if you can hear us, you're ready to start now. Thank you.
Yes, thanks. Hi, everyone. I'm Xueqi Wang. Today, I'm going to talk about improving sandwich variance estimation for marginal cost analysis of cluster randomized trials. This is a joint work with Dr. Liz Turner and Dr. Fan Li. I know that you all know the cluster randomized trial CRT context very well. So I will just briefly start with the context for our work in CRTs. A challenge in many CRTs is usually only a limited number of clusters are available for randomization and implementation, even though the cluster size or the total sample size are sufficiently large. Reasons for including only a small number of clusters include logistical or resource constraints. From the literature, a systematic review of 86 CRTs reported the median number of clusters randomized was 24. And another methodological review of 285 CRTs reported the median number of clusters randomized was only 21. It has been documented that standard analysis of CRTs, like the mixed model or generalized estimating equations with such small number of clusters fewer than 30, tend to inflate type 1 error rates. So small sample bias corrections to maintain valid inference are needed. The bias correction sandwich variance estimators are well developed with a continuous binary or count outcome, and there also exists literature comparing their performances in maintaining valid type 1 error rates. Also, recently, the investigators of these bias corrections have been extended to more complex CRTs with multiple levels of clustering. However, the extensions to sensor time to event outcomes are relatively limited. Especially a recent CRT review from time to event outcomes are not uncommon, but appropriate statistical methods are infrequently used. To the best of our knowledge, there is only one study by Fei and Gruber that performed a simulation evaluation of a specific bias correction. In particular, the marginal cost proportional hazard model is a commonly used model for cluster direct sensor time to event data. It models the effect of covariance on hazard of an event occurrence and targets the hazard ratio as effect measure. Assuming an independence working correlation structure, the marginal cost model has estimating equations derived from the partial likelihood and adjusts for the within cluster correlation through a robust sandwich variance estimator extended from the sandwich variance under GEE. As mentioned before, however, there is limited development and evaluation of bias-corrected sandwich variance estimators for small CRTs with time-to-event outcomes. So to address this gap, we propose 9 bias-corrected sandwich variance estimators for CRTs with red sensor time-to-event outcomes under the marginal cost model. Then we provide practical recommendations based on a comprehensive simulation study. We also develop an R package called BCV, freely accessible on-prem for the implementation of the proposed bias-corrected sandwich variance estimators. Here we have a brief summary of different variance estimators in the table, including the uncorrected sandwich variance estimator and the proposed 9 bias corrections. We first generalized the class of multiplicative and additive bias corrections developed for GEE to the sandwich variance estimator under the marginal cost model. As you may be familiar with this name, such as Fei and Gruber or FG. Then we propose a bias correction based on the martingale residual, considering the features of time-to-event data. Last, given the time-to-event analysis of CRTs concerns incompletely observed outcomes, the challenges in small sample inference can be magnified due to red censoring. And it's likely that each bias correction technique alone may be insufficient. So we hybridize the martingale residual based correction with either one of the multiplicative or additive bias corrections above to further remove the small sample bias. Due to the time constraint, I will not go into the details of the notations or formulas. To implement the proposed variance estimators, The R package we developed is very straightforward. First, install the package called BCV, then given the observed time to event data, censoring indicators, matrix of marginal mean, covariates, and cluster identifiers, the functions can directly calculate the best corrected sandwich estimators. We conducted an extensive simulation study to evaluate the performance of the proposed bias corrections compared to the uncorrected one. We consider a two-arm CRT with equal allocation. We consider a wide range of scenarios with variable numbers of observations per cluster. For each scenario, we generate 5,000 data replications and fit the marginal cost model for each replicate. We consider 10 variance estimators for the intervention effect, the uncorrected robust sandwich variance estimator, and the 9 bias corrected sandwich variance estimators. The results in our simulation suggest to include at least 10 clusters in CRTs with time to event outcomes in practice, especially when cluster sizes vary. When testing the intervention effects, our results suggest the choice of the bias corrected sandwich variance estimator to maintain the nominal test size depends on the variability of cluster sizes. Next, we analyze outcome data from the STOP CRC trial. It's a two-arm parallel CRT comparing 2 strategies for the completion of the colorectal cancer screening with 12 months of enrollment. Randomization was conducted at the level of the health center clinic or cluster with equal allocation to the 2 arms. And we considered the subgroup of non-white participants to illustrate the scenario with a high CV of cluster sizes. We consider a Cox model including only a binary cluster level intervention indicator and compare the uncorrected robust sandwich variance estimator ROB with bias corrected estimators. Because the CV of cluster sizes is larger than 0.4, our simulation results suggest the bias corrected estimator of type KCMR to be used. So here I only show the comparison between ROB and KCMR. This table presents the estimated hazard ratio and the t-test result based on these 2 variance estimators. Obviously, the 95% confidence intervals with KCMR was wider than ROB. Using KCMR, we could conclude that the hazard ratio due to intervention effect is 2. And because the p-value is larger than 0.05, we fail to reject the null of the non-intervention effect. In contrast, if we use the t-test with ROB, the resulting p-value is smaller than 0.05, and the conclusion will be overconfident by rejecting the null. In summary, in this work, we propose 9 bias corrected sandwich variance estimators for CRTs with time to event data analyzed through the marginal Cox model to address the negative bias in the standard robust sandwich variance estimator with a limited number of clusters. And our paper has been accepted by the Biometrical Journal with all information also available online. That's all for my talk, and here are acknowledgements and some references used. Thank you, and I'm happy to take any questions.
Thank you very much for an excellent presentation. Can I just ask if there are any questions online first? Seems not. Okay, can I please ask if there are any questions in the room? Can I just ask then, I noticed you obviously focused on sort of adapting the sandwich variance estimators. Did you look at how they compare to alternative approaches? I don't know, say bootstrapping or other approaches there might be?
Oh, for this paper, we didn't make this kind of comparison, just the sandwich variance estimators, but this can be like an interesting future work.
Okay, sure, thank you.
Thank you.
Final chance, any more questions in the audience? Okay, if not, then thank you again. Thank you very much.
Thank you.
Okay, so our next presentations are here in the room. And first of all is Ehsan from Monash. Over to you. Thank you.
Okay. Hello, everyone. My name is Ehsan. I'm a PhD student in Biostatistics unit at Monash University. And I'm also as a part of the cluster group. And today I'm presenting the impact of removing low information cluster period cells in a sequential manner from step-wedge designs. We know that step-wedge designs have many benefits, but they are usually burdensome and expensive. Suggested to have incomplete designs, which is less expensive and can be useful when the resource for conducting an step-wedge design is limited. In these designs, clusters are not required to provide measurements in all periods and may give us almost the same power as the complete designs. But the thing is that how do we know which incomplete design is highly efficient? And this is the thing that we are interested in this research. And here is the algebraic form of the discrete time decay model that was first introduced in 2019 by Kesta and her colleagues. I could provide some details of this model after the presentation if someone is interested. We know that the goal of each trial is by estimating the treatment effect, and the variance of the treatment effect is used to estimate the sample size and the power. Previous work shows that some cells in step-wedge designs have different amount of information to the estimation of the treatment effect, and omitting some cells has a less reduction on study power. They defined a measure of information contents, a metric of information contents by dividing the variance of the treatment effect estimator from a complete design when a cell is removed to the variance of a treatment effect estimator of a complete designs. I have borrowed some figures of this paper. Some figures of the information contents. The left figure is for 4 periods and the right figure is for a larger period. And values and colors indicates the information contents, and darker colors indicates that each cell contains more information. We can see from these figures that cells around the main diagonal and in off diagonals contain the most information contents or the most information to the estimation of the treatment effect. There are many motivations to continue the information content work, but we were interested in what happens after removing those low information content cells and calculate the measure of the information contents again. Do we expect to see the same pattern as the previous work has found? And another thing is how much efficiency would be lost after removing those low information contents, and how long can we iteratively remove? And are we able to have a highly efficient incomplete designs? So we modified the information content formula, and the previous work looked at one cell at a time, but we considered a pair of cells. So capital A indicates a pair of cells, or they called it in centrosymmetric cells that have the same amount of information to the estimation of the treatment effect. And variance D theta hat bracket A in this formula indicates that the variance of the treatment effect estimator of the design B when a pair of cells are removed. For removing cells in iterative manner, we define an algorithm. And in the first step, we calculate the information contents of the initial design, the full designs. Let's have a look to the example. The left figure is a design matrix of 5 periods, and the right figure displays the information contents when we have 100 subjects per cluster per period, and when the ICC is 0.05 and CHC is 0.95. You can see the pattern is pretty similar to the previous work, but the values are changed because we consider the information contents of pair of cells instead of individual cells. And in step 2 of the algorithm, we are looking for a pair of cells that has the lowest information contents, and we remove those cells. And in the next step, we calculate the information contents for the remaining cells. Suppose that you have a reduced design and each cell contains the information content. So now we iterate the information, we iterate the removal process until we cannot estimate the treatment effect. And this is an example that I have provided. We've removed a pair of cells that has the lowest information content and calculate the information contents of the remaining cells. The next low information contents has been removed. And as you can see, cells distant from the time of the treatment switches are removed first, and cells near the treatment switches remains until near the end. And this is the final design that we can estimate the information contents, because the low information content cells were middle ones. After removing those middle ones, we cannot estimate the information content of the remaining cells. And this is the final design that we can estimate the variance of the treatment effect. And in this slide, you can see how the removal process works. And there are a sequence of the incomplete designs, but the thing is that which incomplete design is highly efficient. So we defined a measure of the efficiency loss that we can measure the efficiency loss of the design at each iteration. And this is the figure of the efficiency loss for the incomplete designs in the previous slides. And the x-axis indicates the proportion of the total number of the cluster period cells that have been removed. And moving from left to the right, more cluster period cells are removed. As you can see from this figure, efficiency loss slightly increased and remains low until the midway point, when 50% of the cluster period cells are removed. And after that, there is a sharp increase in efficiency loss. And also, this is the power of the incomplete designs of the previous slide. And also, there is a less reduction in study power when 50% of cluster period cells are removed. Okay, until now, we looked at one specific example, but here we looked at a more general example. We can compare the efficiency loss for 9 different combination of correlation parameters, or 9 different incomplete designs. What we can see from this figure, all the incomplete designs have the pretty similar results. But if we looked at in details, for example, for the smaller, for the incomplete designs with a smaller CAC, if we look at each block of ICC, we see that the incomplete designs have almost the same efficiency as the complete designs. And when 20% of the cluster period cells are removed, when for the smaller CAC, more efficiency is remained. And when 20% of the cluster period cells are removed, the incomplete designs have almost the same efficiency as the complete designs. And when 50% of cluster period cells are removed, less than 25% efficiency is lost. And we developed a Shiny app to use its interactive features, and we can put different trial configurations and see how the removal process works, and we can compare the efficiency loss and see the study power. What we have found in this research that incomplete designs, when 50% of cluster period cells are removed, can be efficient as the complete designs, and less than 25% efficiency is lost. And there is a small reduction in study power. And these designs look like a staircase designs that my colleague Kelsey will present in the next session. cluster period cells distant from the time of the treatment switches are removed first, and removing cells in the corners of the step-wedge designs, or call it as a hotspot, has a larger impact for exchangeable correlation structure compared to the discrete time decay structure. And cells near the time of the treatment switches are remained until near the end. And some things that we need to consider incomplete designs when measurements with measurements around the main diagonals and possibly in hotspot corners can be highly efficient and less expensive. But because these designs includes hotspots, maybe it is not practical, because some clusters need to provide the measurements at the start and at the end of the trial. And the other thing is that for designing a trial, design efficiency is not the only consideration. And it is good to consider cost as well. So the next project in my PhD will be developing a cost efficiency framework to have a trade-off between the cost and efficiency in the step-wedge designs. And I would like to appreciate all who supported me in this research. And thank you for listening, and happy to take questions. Thank you.
Thank you very much. Excellent presentation. Perhaps I can see first if there are any questions online. No. Okay, so can we throw it open to questions from the audience, please?
Thank you for your presentation. So your future research will focus on taking costs into account. Is this like taking fewer measurements per cluster enables you to take more clusters in a trial?
Yeah,
so if you take so the future direction of your research is about taking costs into account.
To to incorporating cost as with design efficiency, both of them together. And at each iteration now we just consider the design efficiency, but sometimes we need to consider cost as well. So we want to consider both of them.
Yeah, but my question was more like, if you take fewer measurements per cluster, then you're saving money, and that allows you to take more clusters into account, probably. Is that something that might be direction of your future work?
Few measurements, yes. That's
probably I can talk about that later, because it's related to my work as well. So probably be in contact by email or so. Thanks.
I think that was a really interesting presentation. We were also interested in very kind of similar questions about identifying optimal designs like this. One unfortunate thing we found, though, was that sequential approaches, like if you sequentially kind of moved like observations around like a grid like that, or sequentially added them or removed them, there's no theoretical guarantee that actually results in an optimal design, which is really annoying, because this is obviously something we're interested in. But you can put like a lower bound on, or upper bound on, how bad the solution is. So it's just something worth mentioning, I thought, because I think in these cases we sort of ran through loads of different scenarios that most of the time it's kind of fine because it's relatively simple setup. But I thought something worth kind of raising as an interesting point. But I don't know if you looked at other ways of doing it, like perhaps starting with none and then adding them in, or starting with a few and then shuffling them around. I mean, they all have the same problem, but did you look at other approaches?
No, just we just consider removing the low information content cells, but we consider some works in the future to researchers can manually and remove some cells and see the efficiency loss of the design. Thanks.
Thank you.
Thank you. Whilst the microphone goes to the back, maybe I can just jump in and saying, yes, it was occurring to me the same issue, that maybe you can try adding some back in. If you're going to do a sequential thing, you can take out, but try adding in ones you've previously taken out just to check. Please.
Thanks. That was a really nice talk, and I was really pleased to see at the end talking about some of the practical and logistic issues and the cost, because I think that's really important sometimes when we've got these complex designs. I mean, I don't know whether has anybody ever, as you were talking, I was thinking, has anybody ever done one of these incomplete step wedge designs in a trial?
Yeah, staircase designs have been done. haven't they?
Yeah. I mean, I know staircase designs have been done, but you know, you were showing some slightly more complicated things in staircase. And I think the idea of bringing cost into it is a really nice idea and really important to think about those costs that are in the clusters, but also the costs that are out of the clusters, like trial management. And, you know, I mean, there's a lot of stuff that you could bring into that, but I really applaud what you're doing. I think it's great.
Yeah, thanks. Sure. Thank you so much.
Any more questions? Okay, well, thank you again. Thank you. Right. And our next speaker is Kelsey from Monash. Over to you, Kelsey.
All right. Yeah. Hello, everyone. My name is Kelsey. I'm part of the cluster at Monash and very happy to be here. So I'll be talking about staircase designs and how they compare to stepped wedge designs. So something that's been touched on already, but I'll give you a bit more information about them. So most of us are already familiar with the stepped wedge. We've already talked about them a little bit. This is an example of one we might conduct. And in these scenarios, clusters must, from the first period until the last, must collect measurements from subjects and provide that data. And so in some settings, these subjects may be measured more than once, as in a cohort study. But in this talk, I'll focus on settings where each subject is measured just once and new subjects are continually entering the cluster. So stepped wedge designs have a number of advantages. They're appealing in that all clusters eventually receive the intervention. They have this nice gradual rollout across clusters, and they're also fairly efficient. Not sure what's happening to the words there, but you can hear what I'm saying. So they make good use of between as well as within cluster comparisons, which helps with the design efficiency. But one disadvantage is that, as Ehsan mentioned, they can be quite burdensome and expensive to conduct, in that all clusters must contribute data in all periods of the trial. But luckily, because of this recent work on information content, we've seen that not all clusters contribute, not all cluster periods contribute the same amount of information. And so specifically, the cluster period cells close to the time of the switch from control to intervention contribute more than those more distant from the time of the treatment switch. And so this led us to more closely consider staircase designs in their own right as sort of their own design. And so we have a schematic shown here, where each sequence is comprised of just a limited number of pre and post switch periods. So we call this design a basic staircase with just one pre and one post switch period in each sequence. Balanced designs would have equal numbers of pre and post switch periods, or we might have an imbalanced design with, say, one control period followed by two intervention periods in each sequence. And this particular design has appeared a few times in some of the methodological literature as an example of an incomplete stepped wedge. But in this talk, I'll focus mostly on the basic staircase. So staircase designs could potentially be more appealing to participating clusters than a stepped wedge. So clusters would receive the intervention sooner upon commencing data collection. They still have the same gradual rollout of the intervention across clusters. They are potentially much less burdensome, so clusters need to only contribute data in a limited number of periods rather than in all periods of the trial. But one question that sort of remains with these is, how efficient are these designs? So we wanted to better understand the efficiency and the properties of these designs, and also work out how they compare to a complete stepped wedge. The other big motivation is that these types of staircase designs are already being implemented, even without much dedicated methodology. So they're often referred to as incomplete stepped wedges, and the methodology, for a stepped wedge is often used in some way. But in these scenarios, researchers have stated the need to minimize the burden of data collection on participating clusters. But looking a bit into the approaches to sample size and power calculations, the methods that are being used are pretty variable, with a lot of approaches not really being suitable for this kind of design. So the main aims of this work were first to better understand the properties of the staircase design by deriving explicit expressions to enable sample size and power calculations. And second, to compare the efficiency of the staircase to a stepped wedge. So I won't go into too much detail about the underlying statistical model, but we've assumed a mixed effects model for a continuous outcome, where we account for a fixed effect of time on the outcome, the treatment effect, cluster period random effect, and a subject level random error. So as we know, there are several possible structures we might assume for the similarity between outcomes between cluster periods, but I'll be focusing on the discrete time decay correlation structure with which Jess and Ehsan, as well as Sam, talked about in their presentations. So the structure gives rise to this type of correlation matrix where we assume that the correlation between subjects' outcomes within a cluster decay as the time between their periods of measurement increases. And so this gives rise to these two main correlation parameters, the within period intra-cluster correlation rho, which represents the correlation between different subjects' outcomes measured in the same cluster in the same period. And then we have the cluster autocorrelation R, which gives the proportionate decay in correlation from one period to the next. So in order to understand more about the efficiency of staircase designs, we needed to look at the expression for the variance of the treatment effect estimator, which is a key ingredient in sample size and power calculations. So the standard approach to obtaining a variance or a treatment effect estimate is with generalized least squares. And so the expression for the variance of the treatment effect estimator shown here is one that we derived for general staircase designs. And so it's a function of a few different characteristics of the trial and different parameters. So we have number of sequences S, the number of clusters per sequence K, the treatment sequences, which here are just comprised of the zeros and ones for the periods that we do measure within a sequence. We have the covariance matrix for a cluster, which we represent at the cluster period mean level. And then we have the time period effects, which encode the effect for a particular sequence. So this is somewhat useful for sample size and power calculations, but even more useful would be explicit expression that's no longer in terms of matrices. And so this would allow us to make the calculations more straightforward and something that we could more readily interpret. But the issue with simplifying this expression any further comes down to this inner term here, which, depending on a number of things like the design characteristics and the form for the assumed within cluster correlation structure, as well as the assumed effective time, that term requires inverting a potentially large matrix with a non-standard form. But we could obtain expressions, explicit expressions for the basic staircase with just the two periods of measurement. And so assuming categorical period effects, that inner term becomes a tridiagonal matrix, which is still not too easy to work with. But after a fair bit of matrix algebra and using some recent results on inverting tridiagonal matrices, we did finally get there. And we got this expression for the variance shown here. So this is a function of the number of sequences S, the number of clusters per sequence K, as well as A and B, which are the elements in the covariance matrix. So that's A would be the variance and B is the covariance between cluster period means. And so A and B we can represent in terms of either the variance components in the cluster period size M, or assuming a total variance of 1, we can represent those in terms of the correlation parameters rho and R from our model earlier, as well as the cluster period size M. So if we instead assume linear period effects, things were quite a bit more straightforward in the derivation, and we obtained this expression here. So this is just a simple linear function in A and B. So that was quite nice to work with. And when we then substitute the forms containing the correlation parameters for A and B. Then we obtained this expression, which is not quite as pretty, but it's still much nicer than what we would have otherwise had to work with. So looking at this expression, we can then derive a number of quite a bit of information about the relationships between the different parameters and the variance. So we have a little summary here. So just a few of the relationships that we can sort of glean from this expression. As the within period ICC rho increases, the variance tends to increase, although there are some exceptions in certain circumstances with very large cluster autocorrelation R and certain values of number of sequences S and cluster period size M, for which that coefficient in front of rho ends up being negative. As the cluster autocorrelation R increases, or alternatively as the decay and correlation decreases, we see that the variance decreases. And as cluster period size M increases, the variance does decrease, but it does still taper off quite quickly, as we see in other designs. So at some point, measuring more subjects in a cluster period doesn't really help you very much and give you much more useful information about the treatment effect. And the other thing that we found relevant for these basic staircase designs is that the expression that we get is different depending on whether we assume categorical or linear period effects. And specifically, the variance is slightly lower under linear period effects. But this is actually unlike the stepped wedge, for which we've shown that we actually get the same expression depending on whether we assume categorical or linear period effects. So I make that distinction here because not all existing software allows users to specify both forms for time. But given that we know the variance is lower under linear, assuming a categorical period effect would give you a slightly more conservative estimate of your sample size or power. So then just briefly for AIM2, we're wanting to really see how do these basic staircase designs compare to stepped wedge designs in terms of the design efficiency and therefore the required sample size or statistical power. And so to do this, we looked at the relative efficiency, which we defined as the ratio of the variance of the treatment effect estimator for the stepped wedge design to the variance for the staircase design. And so then a relative efficiency greater than 1 suggests that the staircase is more efficient than the stepped wedge. So in this first scenario, we're comparing the embedded staircase design shown on the left to the encompassing stepped wedge on the right. And for these 3 sequence designs, this means that the embedded staircase has just half the total number of subjects with half the number of cluster periods, and for an equal cluster period size, then it only has half the total number of measurements. So we would expect it's probably going to be less efficient than the stepped wedge, but how much less efficient is it? So we're looking at the relative efficiency now as a contour plot for a range of within cluster correlation values. So the within period ICC rho is on the y-axis with larger values corresponding to greater similarity between subjects' outcomes in a cluster period. And the cluster autocorrelation on the x-axis corresponds to the decay, where larger values mean we have less correlation decay. So we can see a few things from this plot, and the big thing is that for the majority of these combinations, the relative efficiency is around 0.7 or 0.8. So even though the staircase design has only half the total number of measurements, it's actually still fairly efficient relative to the stepped wedge. We do see a region in the top right-hand corner where the relative efficiency is a bit lower, down to around 0.5, but generally the embedded staircase is not that much less efficient than the stepped wedge under a number of different scenarios that we might encounter. And in this next scenario, we're looking at the same 2 types of designs, but we now are looking at a larger cluster period size for the staircase design, so that now both designs have the same total number of measurements. So we're trying to sort of even the playing field a little bit between these 2 designs. And looking at the relative efficiency now, there are now broad regions where the relative efficiency is around 1, suggesting that both designs would yield very similar statistical power. But now along the bottom for very small within period ICC values, we see relative efficiencies above 1 and as high as 1.6, suggesting that the basic staircase could be up to 60% more efficient than the stepped wedge design. And one final scenario is another variant of this staircase, which I've called the extended staircase, where it includes additional clusters rather than a larger cluster period size. And so again, these 2 designs have the same total number of measurements. And these relative efficiencies are almost all above 1, suggesting that the staircase can be more efficient and yield greater statistical power for the same total number of measurements. And another way of interpreting this result is that we could feasibly decrease the cluster period size further, or the total number of measurements in the staircase, and still potentially meet or exceed the efficiency of the stepped wedge design. So in summary, a staircase design is a pragmatic alternative to a stepped wedge. It can potentially be much less burdensome and expensive, and the reduced data collection requirements would likely be quite enticing for participating clusters and could even yield a reduced risk of attrition of clusters over the trial. Staircase designs are already being implemented, but these designs really aren't that well understood. And the variance expressions that we've derived for the basic staircase design make sample size and power calculations more straightforward. And when we compared the basic staircase and those different variants to the stepped wedge, we saw that the relative efficiency is highly context specific. So this type of staircase design may be an efficient alternative in some settings, but not in others. And so next we're looking at some other staircase designs beyond the basic staircase to try to see what additional benefits we might be able to get from different types of sequences in these designs. I'd just like to thank my collaborators and funding sources and invite you to ask any questions. Thank you.
Thank you very much. Excellent presentation. Can I see first if no questions online, I don't think. So can we turn to questions from the audience, please? Do we have any?
Thank you very much. It's very interesting. I think one kind of issue it raises is about the timing of the treatment effect. It needs to happen right away for the staircase. So I wonder if you've had a chance yet to consider how you might implement if you needed a washout period, if there's an optimal way to include the washout period and restructure the staircase around that.
Yeah, thank you for that question. That's a good point. And I have seen that in the staircase designs that have already been implemented, a lot of those do have some kind of transition period. So in this work so far, we haven't really incorporated that, but that does seem to be something that at least in practice is quite desirable to allow for the sort of give it a little bit of time for the treatment effect to sort of kick in. So I think that's definitely something that we're going to need to incorporate. And certainly the basic staircase is, maybe a bit risky in that we're only sort of allowing for a short period of time in which each cluster would be observed. So I think also, in these extensions that we'll be looking at, this kind of washout period will be quite important. Thank you for that.
Yes, this is a comment rather than a question, but I think the efficiency gains you're talking about would assume, as I understand it, that the main costs are to do with the measurements rather than the implementing the intervention. If the intervention was expensive to implement, but the measurements were easy, then you probably wouldn't gain much in these designs. Is that fair?
Yeah, I think this is more if the measurements themselves are quite burdensome or maybe invasive, to take on patients, then this is where you'd really be minimizing the burden on the patients, but potentially also on the clusters if it's something that's, quite onerous to sort of keep up each period. So, but yes, given the way that these are sort of set up, there is still that, they do still have to get the intervention up and running. And so that still needs to happen.
Have you looked at whether your results you've presented to extend for like nonlinear models, like binomial or Poisson models?
Not yet, but that is classified under future work. Thank you.
Any more questions? For the break. Come back, please.
Thank you very much. Have you considered to ask a principal investigator how they would welcome such a design? Because in some way it's quite like a before-after study, and each cluster will contribute the same number of participants in both the control and the intervention period. So I suspect that PI would really welcome this design. And I don't know whether you've tried to ask them.
Not yet, but that is definitely on the horizon. We're sort of getting involved in more stepped wedges, and we definitely want to see which of those would be suitable to, conduct as a staircase instead. But I do think, yeah, the fact that these clusters have kind of a balance of control and intervention might be sort of desirable in some cases. So we'll get a better sense of that as we sort of start floating the idea of staircase designs in these discussions.
Thank you very much.
Thank you
once again.
Statisticians are talking about stepped-wedge design. They most often refer to a cluster randomized stepped-wedge design, but a stepped-wedge design can very well also be implemented in individually randomized trial. So I did a search on the internet a few months ago, and these are some examples that I was able to find. I have just been told that in other fields of trials, they use different terminology, by the way, like multiple baseline trial. Okay, so the aim of the study was to find the optimal allocation to treatment sequences. So the underlying model that I used assumes exponential decay correlation structure with a parameter rho and a sustained effect of the intervention. So after the treatment effect switch, we observe the same effect of the intervention. And we also take attrition into account. And in this case, the attrition is constant. So we have an attrition rate equal to R between any two adjacent time points. So the aim was to find the optimal allocation that minimizes the variance of the treatment effect estimator. The optimal allocation was found numerically using the R package Alabama. And I also compared the optimal allocation to the uniform allocation. So these are the results for trials with no attrition. So on the horizontal axis is the rho parameter, and on the vertical axis is the optimal allocation proportion. And as you can see, well, these graphs look quite beautiful, right? So they remind me of the kind of string art that my grandmother used to do in the 1970s. So let's say these are the first art-inspired results that you see here at the conference. So the different graphs are for different number of treatment sequences. And as you can see, the results are quite similar over the number of treatment sequences. So let's have a look at the graph. I guess if I'm going this way, those at home can't hear me any longer. And there's no, there's a mouse moving around. So the highest proportion is assigned to those in the first and the last sequence. That's because we have most information content over there, like in cluster randomized step-wedge designs. And then fewer subjects are allocated to the sequences in between. And as you can also see, the optimal allocation very much depends on the correlation parameter rho. So for a large correlation parameter, the optimal design is the uniform design with equal number of subjects in each of the treatment sequences. But for smaller values of rho, the optimal proportions vary widely over the treatment sequences. And again, with most subjects assigned to those treatment sequences that have their switch at the beginning of the or the end of the study. And so again, this is results without attrition, and then we move on to the next slides. So this is with an attrition parameter equal to 0.05. So between any two adjacent time points, 5% of the subjects drop out. And then the results are slightly different, as you can see. Still, they depend on the correlation parameter rho. As you can see over here, if the correlation parameter is quite small, then the results are pretty similar to what we've seen for no attrition. So highest number of subjects are allocated to those sequences who have their switch at the beginning or the end of the study. But then if the parameter rho increases, the picture becomes a bit different from what we've seen on the previous slide. So this again is without attrition. So here, the order of the sequences determines the optimal proportion of subjects assigned to each of the orders. So the sequence that has the switch at the beginning gets most individuals assigned to it, and then the sequence that has the switch at the end of the triangle gets least subjects assigned, and that applies to any 4 of the graphs. And then we move on to a attrition rate of 0.20, so 20% of the subjects drops out between any 2 adjacent time points. And then the results become even more extreme than on the previous 2 pages. So still for very low correlation parameter rho, those sequences do have the switch at the beginning of the end of the trial, get most individuals assigned. But then if rho increases, then the order of the treatment switch determines the number of subjects assigned to each of the treatment sequences. And as you can see, if you compare those 4 graphs to each other, the most extreme situation is observed if you have 6 time periods. Okay, so in most of these cases, the uniform design isn't the most optimal one. So in the next step, I compared the uniform design to the optimal design. And I did so again for 3, 4, 5, and 6 sequences. And here the different colors indicate the different attrition rates. So the red one at the top of each graph is for no attrition. The blue one in between is for attrition rate of 0.05. And the one here at the bottom, the orange one, is for attrition rate of 0.2. So if there's only 3 sequences, we still have an efficiency of the uniform allocation above 0.90, irrespective of the attrition rate and the parameter rho. But things get a bit different if we have more sequences in the design. So the most extreme situation appears over here. In those, it's very small here on the screen. So for very small values of rho, the relative efficiency may be as small as 0.80. And then over here, you see that again, the efficiencies depend on the parameter rho. And here we find an optimal for the efficiency. Okay, so again, this is all about individually randomized trials. And of course, in my future research, I'll extend this to cluster randomized trials as well. So there we can think about cohort designs or cross-sectional designs. We can think of complete clusters dropping out or individuals within clusters dropping out if we're talking about a cohort design. But still we can do the same kind of research for cluster randomized trials. So that concludes my presentation. So are there any questions? I think I'm right on time, right?
Is this microphone on? Yes. Any questions? First of all, at the back, are there any questions from people online? No? Okay. In the room? I'll come to you. Can I start with a question, Mirjam? So in some of these graphs, there's quite a lot of sensitivity to the attrition rate in terms of what the figures look like. If you're thinking about designing a trial, do you have in mind that you would consider a kind of a range of possible attritions and think about the design implications of that?
Yeah, it could be an option. Yeah, I haven't thought about that, but yeah, it could be an option to take into account. Yeah, and so of course I always advise people coming to my office for advice to have a look at similar studies in the past, but most often they don't have time to do that. And if they do, they most often be not able to find anything similar. As you know, I'm working in social sciences, so we don't replicate each other's studies so very often. Yeah, but it would be nice to have for instance, an overview of what could be reasonable attrition rates and of course also reasonable values of the rho parameter.
All right. One more quick question from Andrew.
Thanks very much, Mirjam. I'm just wondering, with attrition, we're essentially talking missing data arising there. So you're thinking of incorporating some missing data patterns based on trajectories so far, etc., rather than essentially you were just assuming the attrition is sort of completely a random Is that right?
Yeah.
Yeah.
Keep things easy, right?
Yeah, of course. And yeah, of course, and start with
Yeah, completely as random.
Yeah, because we don't. I suppose when clusters drop out, there's all sorts of reasons.
Yeah, I can imagine very well if they have to wait long for the treatment switch, they are more likely to drop out. Or probably the other way around, that they are eager to stay in the study because they're still waiting for the treatment to become implemented. Yeah. I can work for future research.
Thank you very much again, Mirjam.
Thank you.
Our next speaker is Laura Etfer. Move the presentation onto yours.
Right, so this is part of work that I'm doing as part of my PhD. It's an optimal allocation. We're back in the cluster world. So yeah, it's stepped wedge. By 3 p.m, I'm hoping everyone knows what stepped wedge is, so I won't go on about this, but to start off a little existentially, what is the point? So talking about optimal stepped wedge designs, what I'm generally referring to is minimizing the treatment effect variance. In terms of allocating sequences to cluster, this is something we have guidance on for designs with normal outcomes. But for binary outcomes, this isn't something that we have guidance on. Kind of as soon as you're looking at designs with binary outcomes, you see that there's your model parameters start to appear in your variance covariance matrix, and you need to deal with that somehow. You could pluck numbers from thin air, but that doesn't usually give you a very robust model. So my approach is to adapt some existing methods. So there is this paper, which does selecting optimal sequences just in the realm of individually randomized crossover trials. So I looked at this paper, and what it does is it uses Bayesian optimization. You have prior distributions on those model parameters that I just mentioned were causing you issues in the variance covariance matrix, and you use those to estimate a weighted average for the treatment effect variance, which you can then pick the sequence allocation to clusters that minimizes this treatment effect variance. All the analysis of the trial is assumed to be through GE, so the optimization is Bayesian, but all your actual analysis of the trial is still frequentist. And yeah, correlation between clusters is then modeled by a working correlation structure, and we looked at independent, command symmetric, and autoregressive. So the dependent parameters that we're putting into this model is we have the number of periods, R, which is to do with the correlation, and I think it's what Jess referred to as the cluster autocorrelation. We have the period effect and the treatment effect, which is what we have priors on. We have the ICC, the cell size, so the amount of people in a period cluster. And then I looked at kind of several examples of trials to simulate, but we'll be looking at one which is a scenario that was investigated in a paper by Barker et al., which will be in the references that I used for this. So in that example, we have 13 periods, an ICC of 0.05, a cell size of 50. For our period effect and treatment effect, in that same paper, there is also a method for simulating data from a stepwise trial with binary outcomes. So we use that to then estimate a 95% confidence interval for those parameters, which are used in the prior. And for the results I will show you, we're assuming an autoregressive correlation structure. So yeah, this would be compound symmetric, and this would be autoregressive. So I've only looked at so far at varying R. You could vary all the parameters, but as you can see, if we look at R equals 1 along the bottom, we see that you can't see on the screen as well as I can see on my laptop how it changes. But there's at 1, in sequence 1, there's 0 allocation. There is some allocation in all the kind of ones in between, though it isn't equally allocated, and the majority of clusters allocated to sequence 12. What you can't see is that as you increase R, more allocations start kind of coming into the middle clusters here, sequences even. Yeah. So yeah, if you didn't want to do all of that, what we looked at is using a Bayesian way to tackle this. If you didn't want to do all of that, you could potentially look at the existing work that exists for normally distributed data and try to approximate it. So just as an example, the results by Laura et al., which are these. This is the sequence allocations for clusters. So for sequence 1, and here that would be 12, the last one, clusters are equally allocated to those, and in 1 and 12 you have more than in the middle ones, which also have equal allocation. And this assumes an R of 1. So if I put that in the corner, you see that, well, you don't, but what you should see is that, but sequence 1 doesn't have any allocation, whereas in the normal approximation it does. And then all those have equal allocation in the normal, whereas in my method, those vary. So the next question would be kind of, what is the tipping point? How wrong can you be about kind of the parameters you put into the normal approximation before it's kind of not giving you reasonable answers compared to kind of the method that I'm proposing? And here are some references. Thank you.
Thank you, Laura. Are there any questions? Let me get out of the light. Questions online? No questions. Lots of questions in the room. So I don't know who was first.
Hi, thank you. So when you say you're identifying the kind of optimal design there, what say algorithm or method are you using to identify the optimal design?
Yeah, so it's been a while since I've looked at the code, but it's like it's integrating let me figure it out. I do remember.
But no pressure.
Yeah, so you have the treatment effect variance, and you do some kind of integration, which I can't remember because the code does it, and it's actually the log of the variance that I'm minimizing in there. But if you email me, I can actually.
Does the elfing, is that the word involved in it?
Sorry, could you say that again?
The word elfing, Elfing's theorem. I sort of, well, I don't know. It's one way of doing it. I wondered if that was the way you did it.
No, but I can't remember the exact thing that's happening.
Thanks, Laura. That was a really nice presentation. I noticed that you get non-symmetric allocation of clusters to these sequences. I'm wondering if you can provide a bit of intuition around why we see that sort of pattern. Is it maybe due to changing prevalences over time?
Yes, so there is kind of the effect of time in the priors that could be driving it, because that kind of plot does look different for like different examples. I've also looked at expedited partner therapy trial, and that kind of doesn't have as dramatic kind of changes. So I would have to kind of have a play around with all the other parameters, like the time effect, to really answer that.
Thank you.
Thank you. Okay, well, thank you very much again, Laura. So we're going to return the program back to presentations in the room. I hope I can now reverse where we were to get to Caroline Kristunas' presentation, which we missed earlier.
Thank you, Richard. Tough act to follow. So this is some work that I've done alongside Fanley and Carla Hemming, looking at small sample corrections for linear mixed model analysis of step-wedge cluster randomized trials using a simulation evaluation. So I'm going to start with a bit of a motivation for why we've conducted this work, and then talk through some of the small sample correction methods that are available in the literature, talk through the simulation evaluation that we conducted, the results, and then some limitations in future work. finished with some conclusions and recommendations. So stepwise trials, very much like parallel cluster randomized trials, often randomize only a small number of clusters. So median number, the systematic review identified in 2016 was 17 clusters, with the interquartile range ranging from 8 to 38 clusters. So although we know in an ideal world, we need a certain number of clusters in order to be able to do a good evaluation. So for cluster randomized trials, there's been a recommendation of at least 40 clusters in order to ensure that we don't lead to analytical biases arising from violations of our model-based assumptions that often rely on large sample approximations. And these then lead to incorrect type 1 error rates. But in reality, quite often these stepwise trials are being used because they are efficient and we can get away with only using a small number of clusters. So to account for this, very small sample and for mixed models, this is often degrees of freedom corrections have been proposed for linear mixed models, but these have not been evaluated for stepwise trials. And unfortunately, they often aren't actually used in practice either. So some of the examples that are available in the literature and the most commonly used examples have been investigated for parallel cluster randomized trials by Kristunas and others, and they compared the performance of 3 different degree of freedom corrections for parallel cluster randomized trials in comparison to some uncorrected methods. And they made some recommendations based on the number of clusters. So for mixed models between 4 and 8 clusters being randomized, they recommend using the between within correction. So this is a design-based correction that's often the number of clusters minus the number of parameters that are being estimated by the model. For between 10 and 20 clusters, they recommend using a status weight correction. And then between 30 and 40 clusters, either the status weight, the between within, or also the Kenwood-Roger corrections have been recommended. Jennifer Thompson and others investigated looking at combinations of standard error and degree of freedom corrections for generalized estimating equations. So here we have the availability of using different combinations of corrections, both to the standard errors and the degrees of freedom. And this is for stepwise trials. And they considered 2 status weight type degree of freedom corrections in conjunction with 3 design-based corrections. So this included the between within degrees of freedom correction, but also methods that take into consideration the number of cluster periods that we see in the step-wedge design. So in our simulation evaluation, we considered these methods that have been used in parallel cluster randomized trials and also the degree of freedom corrections that have been looked at for generalized estimating equation analysis of stepwise trials. So these all use a F test as opposed to a Z test in the uncorrected analysis. So we looked at the Kenwood-Roger and Satterthwaite degrees of freedom corrections. And then the 3 design-based ones we looked at were the classic between within, so the number of clusters minus the number of parameters. We also looked at the number of cluster periods minus the number of parameters, and the number of cluster periods minus the number of clusters minus the number of parameters. So to keep things simple, data were generated from a linear mixed model, assuming no treatment effect, a random cluster effect, and a fixed 0 time effect, with an exchangeable correlation structure. Data were then analysed using a linear mixed model fitted in R by Remel approximation with random cluster and a fixed time effect. The treatment effect was then tested using each of the proposed small sample corrected methods, and this was replicated 10,000 times, and the proportion detecting a treatment effect at the 5% level was calculated using the Monte Carlo type 1 error rate. So we looked at 9 different designs of stepwise cluster randomized trial with between 6 and 16 clusters. We then varied the number of periods between 1 cluster per sequence or 2 clusters per sequence, up to 16 clusters where we had a few more options. So we were looking at 4, 8, or 16, or 8 for or 1 cluster per sequence. And then we also varied the total cluster size. So for the smaller numbers of clusters, we were looking at cluster sizes of approximately 200 in total across the whole trial. And for the slightly larger numbers of clusters, we decreased this to approximately 100 individuals per trial. And we looked at 3 values of the intracluster correlation coefficient, 0.01, 0.05, and 0.1. So to start with, the clusters minus the number of parameters degree of freedom correction performed very poorly. It often gave a type 1 error rate very close to 0% and no greater than 3%. So I've omitted the graphs for those. But as expected, the Z-test and had an inflated type 1 error rate with values as high as 7.1%. And the Satterthwaite correction actually didn't perform much better, despite being one of the better performing methods in parallel cluster randomized trials. So you probably can't see it on the screen there, but I have included the 95% confidence interval for the Monte Carlo approximation. So that runs between about 4.6% to 5.4% roughly. So it's basically just when the ICC is particularly large, the type 1 error was well maintained, but otherwise we ended up with quite inflated type 1 error rates in both these instances across all of the different designs. So the other design-based corrections were on average unbiased. So I think you can probably see better where the 95% confidence interval lies here. So it's in this middle section. So on average, we ended up with approximately 5% type 1 error rate. However, the performance was related to the number of cluster periods and also the ICC. So in both these instances, when we had I think it was more clusters being randomized to each sequence. As the ICC increased, we ended up with conservative type 1 error rates. And when we had fewer clusters per sequence and smaller ICCs, we tended to get more inflated type 1 error rates using both of these design-based corrections. So overall, the Kenwood-Rogers correction was also unbiased on average, but it also performed very consistently across all of the designs and the scenarios that we considered, with values confined between 4.4% and 5.5%. So only just sneaking outside of our Monte Carlo 95% confidence interval. So just in these instances where we've got, so I think this is the design with 16 clusters and 5 periods, which seems to be one of the more extreme designs that sort of sneaks out of this, and design with 16 clusters and 5 periods again. But overall, the Kenwood-Rogers correction performed very consistently. So in terms of limitations for our evaluation, we have considered only a limited number of scenarios, which does exclude the presence of a time effect. And we're only considering really an exchangeable correlation structure. So it'd be interesting to see how these methods perform when our design becomes a little bit more complicated. And further investigations are also needed to explore the use of these small sample corrections and their effect on power, as has been investigated in parallel cluster randomized trials designs, where we find that the use of these corrections does tend to lower our power. So it needs to be considered when we come up and when we're considering our sample size calculation for the study. So to conclude, stepped-wedge trials are at risk of inflated type 1 error rates when randomizing 16 or fewer clusters when we're considering a linear mixed effects analysis. We do recommend that a Kenwood-Rogers degree of freedom correction be used in the linear mixed model analysis of stepped-wedge trials, randomizing small numbers of clusters. And I'll leave you with some references. Thank you.
Thanks, Caroline. Do we have questions in the room or on the Zoom call? Questions in the room?
Thanks, Caroline. Really interesting that your results were so different to my GEE results, where clusters minus parameters was best. I'm sure you did. Did you adjust for time in the analysis model, even though you simulated no time effect?
Yeah, it was considered as a fixed effect.
Okay, thanks.
Thanks for the presentation. I also have a question. Would you also recommend methodologies for parallel group cluster randomized trials?
So Clemence's paper looks at parallel cluster randomized trials in more detail, and she only recommends Kenwood-Rogers when you've got a large number of clusters, so in the 30 to 40 range. So generally across the board, Satterthwaite tends to perform a bit better. So part of the motivation for this work came from looking at doing a simulation study. So developing methodological work, doing a simulation study where we were considering scenarios where we had small numbers of clusters, because obviously that's the scenarios that we're often looking at, and realized that the Satterthwaite didn't look like it was necessarily performing as well as it does for parallel designs, which motivated looking at this work and finding that actually Kenwood-Rogers seems to perform much better.
Okay, thank you. I'll check out that paper.
I think, oh, Andrew.
So really quick. You mentioned a comment about taking the Kenwood-Rogers degrees of freedom into account in sample size calculations, but you don't know, they depend on the variance, the observed variance components. Are you aware of any work, has anyone sort of put in your design, like you've got your cluster variance and error variance, plug those in to see what the Kenwood-Rogers degrees of freedom might be for design purposes?
Not that I'm aware of, no.
No. Yeah, okay, that'll be interesting.
All right, well, I think we should move on with the program. Thank you very much again, Caroline. So the last section of today's program is just a couple of notices. I think Chris is going to come and help me with loading them up. Right, so a couple of notices or announcements. The first of these, Andrew Kopus mentioned this in his talk. I wanted to bring people's attention to some newly advertised PhD opportunities, which are set up by the Trials and Methodology Research Partnership in the UK, but they're open to people globally. If you want to find these PhD opportunities, they're on the Find a PhD website. If you go to the Find a PhD website and you search on that site for TMRP, you will find a number of these methodology PhD studentships. So if you know any students, or if you yourself are looking to do a PhD, do direct them to these. In particular, there are at least 3 which have some sort of cluster randomized or stepped-wedge connection. One of those was Andrew Kopus's, which he mentioned in his talk, and there are 2 others based here at QMUL. So I would want to draw your attention to those, obviously, and please do apply for those, or if you know people are interested, please do direct them to those opportunities. For the next bit of the announcements, I'm going to pass over to Jenny.
Thank you, Richard. This is a very quick plug for a website about cluster randomized trials. So I'm Jenny Thompson. I'm one of the editorial team members for this website. For those of you doing trials, it's a really useful place to find resources about how to design, analyze, and report your studies. And for those of you doing methodological research, it's a useful place to find methods papers that might be useful for your methods research. Oh, and also a great place to increase the impact of your research if you're doing methods work. So what is this website? You'll see it, the heading here, and at the top we have some sections. We've got an introduction, resources page, a notice board, who we are, and a contact us page. The introduction and resources pages are split into sections on parallel cluster randomized trials and stepped-wedge trials. In the stepped-wedge trial sections, we have a small amount of information on cluster crossover trials. The introduction's what you think it would be, some basic description about what these trials are, some papers and textbooks for the first things that you should consider if you're doing one of these trials. But I expect if you're at this meeting, you probably already know most of what's on the introduction pages. But maybe you know about parallel CRTs and not so much about step-wedge trials, in which case the introductions would be a good place to start. Most of the information's in the resources section. So the resources are split into design, analysis, and reporting. Here we're in the parallel cluster randomized trial resources page, looking at design topics. Each of the purple sections on the page will expand to give you a bit more information about that topic. So if we look at the ethics section of the design for parallel cluster randomized trials, you have some basic text about why ethics are different in a cluster randomized trial, and then some links to papers that can give you a bit more information on that topic. And you can click on the underlined text of the paper to be taken to that resource. So other design topics are sample size, randomization, preventing bias, and there's a list of tools and software that might be useful while you're designing your trial. In the analysis section, we have types of analysis, types of outcomes, how to deal with a small number of clusters, missing data, and analysis dealing with causal inference. And then there's a reporting section which lists all the relevant guidelines and reviews on how well trials are currently being reported. Next, we have the notice board, and this is where we advertise events like this conference and training courses and other news like research articles that have just been released and job advertisements. And lastly, we have a section of who maintains the website. So it's being maintained currently by a group of 8 researchers: Claire Chan, Sandra Eldridge, James Martin, Melanie Prague, Carla Hemming, Clemence Lerat, me, and Liz Turner. And we each lead a different section of the website. And some of us are here today and tomorrow if you'd like to chat to us or have any questions. And then lastly, but most importantly, there is a contact us page where you can contact us if you have research articles or tools which you would like to be added to the website. I've seen a few here today that I think we might be adding to the website, or events or news you would like us to advertise. So you can use the contact us page or the web address shown on the screen here. And it's really helpful if you get in touch with us in case we've missed anything important that would help keep the site up to date and useful for people doing trials. And lastly, if you'd like to join our editorial team, we're always looking for new members to help out. Again, contact us either on the website, the URL's at the bottom of the screen, or use the email address shown on the screen as well. It's quite a low workload and just involves periodically checking for whether there's any new papers or information to be added to keep it current and up to date. That was all I had to say in my brief announcement, and if anyone has any questions, happy to answer them. But if not, we can all.
Any questions for Jenny? No, well, I think we're through. You've done it. You've made it through the first day of the program. Thank you all very much indeed. I'll let you go and enjoy what's left of the, I was going to say sunshine. Go and explore Whitechapel and London, or get over your jet lag. And I look forward to seeing you all again tomorrow.